So this is the assignment which is related to nuclear physics. We have discussed the first 15 questions from this. It's an important topic, so it's better like you should have a bit good practice of these questions. We did till question 15. In question 16, a radon gas, which is naturally occurring radioactive gas, is there. Means it emit out, because some are artificial radioactive element, but radon is a natural radioactive element. So radon 222 decay by polonium by emitting out an alpha particle. So 4 and 2 will be there. Whenever there's an emission of alpha particle, the nucleon number decreases by 4 and the proton number decreases by 2. So this will be 86. Give two reasons why radon is particularly dangerous. So why the radio, basically what will happen as why the gas or radioactive materials are dangerous, as they're emitting out radiations, like as it's emitting out alpha part. If any source of alpha is inside the body, it is dangerous as compared, because alpha cannot penetrate through like 4 to 5 centimeter in air or through our skin. But as radon is a gas, so and it is there in the atmosphere, so as gas we breathe in, so it enter in the internal, like it's entered or it's inside the body. And when alpha source is inside the body, it is dangerous, can cause, as alpha is high ionizing power, so it can enter the body like it is inside the body. As a result, what will it will do? It will cause ionization. And when alpha source is greater ionization, so when alpha source is inside the body is dangerous as compared to it is outside. The total kinetic energy of alpha particle and the polonium is 5.59 mega electron volt. Calculate the mass difference in kilogram between the nucleus of a radon and its product. So we have to calculate the mass defect. Basically what happened, like the mass defect is actually converted, like the radon is having a mass, like example M1, the alpha particle in polonium is having a mass M2. The difference in the mass converted into energy, like M1 minus M2, will be the mass defect. And that mass is actually converted into energy. And which form of energy it has converted into? It converted into kinetic energy. So we have this energy. So we can use the formula E is equals to mc square. So we have the energy, we have the speed of the light, then we can just square and work out the mass defect. But energy should always be in joules, but this energy is given in mega electron volt. So we don't have to calculate the difference in masses. Actually, the difference in the mass convert into energy, and that energy is the kinetic energy. So we have the energy equals to the mass defect times speed of light. But energy should always be in joules, not in mega electron volt. So if we have 5.59 mega electron volt, so means 10 power 6. And to convert electron volt into joule, so we have to multiply by 1.6 into 10 power minus 19. So delta M, and then speed of light is 3 into 10 power 8 and then square. So we just simplify and get the value for delta M, which will come out 9.9 exponent minus 30. 9.93 into 10 power minus 30 kg is the mass defect, or the difference in the mass between the reactant and a product. And this mass is actually converted into energy, which is equivalent to 5.59 mega electron volt. Is it clear, this one? In part C, in some home, the activity of the decay of radon can be very high, as 1000 becquerel for each cubic meter of air. Like if we have a certain amount of 1 meter cube of air sample, this much is the activity. Radon has a half-life of 3.3 exponent 5. Calculate the number of radon nuclei in a cubic meter of air with an activity of 950 becquerel. So what we have to do, we have the half-life, so we can find because how the half-life or the number of atoms are related. So we have the formula n is equals to n naught e raised to power minus lambda t, or you can also say a is equals to a naught. So activity itself is equals to n lambda, where n is the number of the nuclei present and lambda is a decay constant. Like how many nuclei emitted out every second, that is known as activity. So first, using the half-life, we'll get lambda. Then we want to find how many atoms are there with an activity of 950. So this is what is required. N is required. So first we work out the lambda. So lambda is equals to 0.693 divided by T half, because T half is 0.693 lambda. So lambda is 0.693 divided by T half. So this will be 0.693 divided by half-life 3.30 into 10 to the power 5. This will be 2.1 into 10 to the power minus 6 seconds inverse. Lambda is always second inverse. So we got the lambda. And we already have the activity, that is like 950 becquerel, that is activity. And it's like how many nucleus decay every second. So A is equals to n lambda. A is the activity 950. N we don't know, and the lambda we already worked out 2.1 into 10 to the power to 10 to the power 6 minus 6. This was minus 6. Then we simplify for n, like we divide, so we'll know it's about 4.5 into 10 to the power 8 atoms are present in this sample. So this is always the formula if you need a number of atoms present with an activity. Now, it is recommended that the radon level should be reduced in a home where average activity of a cubic meter is 200 becquerel, greater than 200. Calculated time, it changes. So original activity is 950 and new activity is 200. So A is equals to A naught e raised to power minus lambda t. A is 200, A naught, the original activity 950. Lambda we already calculated in the previous part, which was 2.1 exponent minus 6. And T we are finding. So this 200 divided by 950 e raised to power minus 2.1 into 10 to the power minus 6 and T. And then we, to cancel this E, we take ln both sides. So it will be ln and here also ln. This we work out like 200 divided by 950 ln, and this ln and E will cancel. So we are left with minus 2.1 into 10 to the power minus 6 into T. But this is ln 200 divided by 950. So using a calculator, you work out this value, it will be negative. So ln 200 divided by 950, the final answer negative, and this whole factor is multiplied, other side divide. So you will get the time, it is about 7.4 into 10 to the power 5 seconds. So this much time it will take to change its activity from 950 becquerel to 200 becquerel. The risk to people increases as the concentration of a radon in a home increases. However, about 90% of the death caused from exposure of a radon gas occur in home where the activity is less than 200. So just why this is the case. Like What is the reason for that? Like the risk to a people increases as the concentration of a radon gas in the home increases. And however, about 90% of our deaths which caused from exposure to radon occur in a home where the activity per cubic meter is less than 200. Like even activity is not even very high, but that can lead to a death. Suggests why this is the case or why this happened. So because there are many household devices which are using like or we have might have a trap radon or the home is not perfectly ventilated, that may lead to a death. So this is an open response question. You can write many answers are there related to this, but the main is like any activity which you explain that it causes the concentration of a radon to not change or increase. Like if a room is not ventilated, that may also leads to that may also leads to a death due to a radon as a concentration increase. In part D, the sample of a radon is placed in a sealed container. Initial activity is measured. The student calculate the value inside a container after time equal to 2 half-life. However, the measurement of activity inside a container give a value considerable higher than this. Why the student calculation does not agree with the measurement? Because what happened whenever like radioactive element decay, as you can see, a radon is decaying into polonium. So this polonium might be also radioactive. So that also it start to emit out radiation. So that's why, like example, what we are considering we have a radon and the which is a source of the radiation that is emitting out radiation. But when radon convert into polonium, that's also a radioactive, so it's emitting out radiation. So practically, like if we were having say 800 becquerel, after half life it should be 400 becquerel, but practically it won't be 400. It might be like 600. What might be a reason to have a higher value than what is expected? Because the product which is formed might also be a radioactive. And this is what normally happen, that the radioactive sources, when the product is formed, that is also a radioactive. That's why after a half life we don't get the same result what we expect. And in question 17, the graph shows how the binding energy per nucleon for a range of isotopes are there. So you can see the iron occupy like the highest binding energy per nucleon is for iron, Fe, the most stable nucleus. So explain why alpha particle or a helium nuclei is more likely than other small nucleus to emit a large unstable nucleus. Means why the alpha particle, basically all these atoms tend to gain the stability, the nuclear stability, by making the highest binding energy per nucleon. So binding energy per nucleon for like what they mentioned, why an alpha particle helium nuclei is more likely than the other smaller nucleus to be emitted from a large unstable nuclei. So when we have a large unstable nuclei, why they emit out alpha particle likely like this one? As you can see, compared to other lighter atom, it's having the highest binding in it compared to other lighter atom. Like why likely this might result in helium or they might result in helium first. It is a like first hydrogen to helium, then helium to carbon, then to nitrogen. So what is the reason for that? So binding energy per nucleon for helium is greater than compared to other small nuclei. So as a result, the and when the binding energy increases for one to another, the energy will be released by the nucleus will be greater. And the helium nuclei, as it's having a higher binding energy per nucleon compared to other lighter atoms, so it is likely to be stable. So 2 points. One is compared to lighter atom, this helium-4 is having the highest binding energy per nucleon. So when they fuse together, they result in a formation of this helium, which is having higher binding energy or greater stability. Explain why the fission reaction use isotope of uranium-35 your answer should include reference to the graph. Like why we use for fission, why we use uranium 235. First thing, if we use urine, like it has to reach iron here. So they have a greater gap. When the greater gap is there between the binding energy of the reactant and product, more energy will be released. If there was a smaller gap, then small amount of energy will be released. So the, from this graph, we can identify that there's a greater gap between binding energy per nucleon for helium and iron. So when it undergo a nuclear fission reaction, like it break down into a lighter, it release more energy, so it will make it more or suitable for as a nuclear fuel. Like release, because when we use something as a nuclear fuel, it must release energy, and this will release more energy as compared to others. Is it clear this part?